Part C. Write but do not evaluate an integral expression for the volume of the solid generated when r, so that's this region right over here, when r is rotated about the horizontal line y is equal to 1. So y equals 1 is right over there. So the way I'd like to think about it, let's think about what the volume, if I were to just take the bottom function, if I were to just take f of x, and if I were to rotate that function around y equals x, if I were to rotate this thing around y is equal to 1, what would the volume of that be? And then I'm going to subtract from that the volume if I were to take the top function, if I were to take g of x and rotate it around. So let's first of all think about what volume I would get, and this is really the disk method, and I go into it in much more detail earlier in the calculus playlist. But let's think about the volume if f of x is rotated around that axis. And to do that, let's imagine each sliver of that volume. So this is, let me draw a little thing right over here. And you can imagine once this little sliver is rotated, it forms you can imagine this length is the radius of a disk. And just to imagine that, let me draw the entire disk. So if this is rotated around, it will become a disk. It will become a disk that looks something like that. And I'll just call the depth of the disk. So the disk, if you imagine a coin, this is kind of the side of the coin, the depth of the coin. The depth of the coin right over there. I know I can draw that better than that. So the depth of the coin is just like that. It's a fixed depth. And I'm going to call that dx. So it's just this distance right over here. It is dx. And what is going to be the area of that coin? Well, the area of the surface of this coin, so let me do it like this. I want it in a different color. So I want to do it in blue. The area of this coin is just pi times the radius of that coin squared. And what is the radius of the coin? Well, the radius of the coin is this height right over here. And what is that height? Well, it is 1 minus f of x. So that is equal to the radius. So the area, the area of kind of the face of this coin is going to be pi. The area of the face of this coin is going to be pi times the radius squared, which is equal to pi times 1 minus f of x, 1 minus f of x squared. That's this blue area right over here. And then if I want to find the volume of this coin, I would multiply it by the depth of the coin. So times dx. And if I wanted to find the volume of this entire solid, this entire rotated solid, I would want to find the sum of all of these volumes. So this is just the disk right over here, but I could have another disk, a similar disk that I do right over here. I could have another disk right over here. And I want to take the sum of all of those disks. So I want to take, so the volume is going to be the sum over all of those disks. So x goes from 0, which is this bounding point, to x is equal to 1/2, times pi times 1 minus f of x squared. This is the area of the area of the face of each of those disks. And then I multiply it times the depth of each of those disks. Now this is the volume of each of those disks, and I'm taking the sum of all of them. So this is the volume. This is the volume if I were to just rotate f of x around y is equal to 1. And actually I should just write dx here. And so this right over here, this expression, I just did that so they really are equal. This is obviously just the volume of each of those disks. So this is a volume if I were to take the f of x around y equals 1. Let's figure out, so let me call this volume of f of x. And by the same logic, the same exact logic, we can figure out the volume if we take g of x. If we rotate g of x around, if we construct disks like this and rotate them around y is equal to 1. And so the volume, if I take g of x around y equals 1, would be 0 to 1/2 times pi times 1 minus g of x, because 1 minus g of x is each of these radiuses right over here. Each of these radiuses. That squared dx. And so the volume of what they're asking us, the volume of the solid generated when r is rotated, well, r is kind of the space in between f of x and g of x. So it's going to be, the volume is going to be the difference between these volumes. It's going to be this volume this is kind of the outer volume, and we're going to take out its hollow core. We're going to hollow it out by subtracting out this volume. So the volume of that region is going to be the integral, I'll do this in a new color, integral from 0 to 1/2 of pi times 1 minus f of x squared dx minus the integral from 0 to 1/2 of pi times 1 minus g of x squared dx. And this is a completely valid answer, but you might want to simplify it. We have the same bounds of integration. We have the same variable of integration. And actually we have this pi over here, so we could factor that out. And so this is the same thing as pi times the integral from 0 to 1/2 of 1 minus f of x squared minus 1 minus g of x squared, and then all of that dx. And actually you probably would want to do this. You probably would want to do this if you're taking the AP exam, not just leave it in terms of f of x and g of x. You would actually want to write the expressions for what f of x, and g of x are. So really the best answer would probably be pi times the integral from 0 to 1/2 times 1 minus, well, f of x is 8x to the third power, 8x to the third power squared, minus 1 minus g of x. G of x is sine of pi x, that squared times dx. And that would be our answer. And you can see why they didn't want us to go through the trouble of evaluating it. They just wanted us to set up this integral